Alright, welcome. I've got an action-packed event for us today. There's a lot of cool things. I'm going to talk about more details on compilation. We're going to talk about how code gets optimized. It's very, very cool, and we'll learn a lot of things. I'm not quite sure how I want to test you on this, though. Let me just promise this right now. If I test you on anything from this lecture, it will be an easy question that you can probably just go back to my examples and read off. Okay? That is my guarantee to you. So I am required to teach you a lot of things, and this is the lecture for them. All right, I've got a bunch of pre-made code, because the code isn't really the issue this time. It's more like what we're going to do with the code, all right, if that makes sense. So let's first talk about compilation, all right? All the things that I've kept swept under the rug, let's talk a little bit more about it right now, all right? So there's something cool called the preprocessor, which maybe you've interacted with slightly when you've included files and stuff like that. So C and C++ are some of the languages that have a pre-processing stage before the actual compiler does something. Okay, so this is what's going on. You start with your CPP file, your source code, and then your source code has some includes in it, right? Some includes, maybe some defines, things that start with number signs that aren't actual C++ code, right? Because there's no semicolon. All those things. That's for the preprocessor, actually. Every line that starts with a number sign, they're special, and it's going to mess with the file after the preprocessing stage. It's going to expand the code into something different, all right? And then it's time for the compiler to actually do its job and emit assembly code. And then you've got a bunch of object code after that, and you'll link them together. Okay, so that's kind of the process. A little bit more detailed, but let me show you an example of how to look at that pre-processing stage and see what's happening. All right, I'll use an example of a program with a library, and it includes that library. So here's my silly example. I don't want to show you include IOStream because you can imagine the IOStream header file, if it's going to get copied and pasted, then it's just going to be giant. It's going to make the whole file giant and hard to read. So here is my first pre-written code. I've got these 3 files. Let me walk you through it. So I've got a main.cpp file that just calls a square function. All right, calls a square function, and let me do it this way first. Actually, let me not use this define. I'll add it right back. All right, I'll call square with 42, and where does that square function live? Well, it's declared in this header file, square, and then it is implemented here in the CPP file. So if I can show them all to you at once, I will. I think I can. Boop. So there's header file, and then you got implementation file. I think that works, right? So they're all working together, and we got some include lines. Those number sign lines mean preprocessor directive. So do something. This is not actual C++ code yet. It's something for the preprocessor. And we can watch the preprocessor work by doing G++-E. Okay, G++-E, and we're going to give square.cpp, square, excuse you, I'm in the wrong folder, square.cpp, main.cpp, and I think that's it, and -e though. And what that's going to do is it's going to spit out what it's going to compile, all right, what it's going to send to the compiler, if that makes any sense at all. And yeah, let's try and zoom in on that idea. So there's the header file. It's got some if and defs and defines. Those are also going to go away, right? But I won't talk about those too much. But this includes square.h. Let's watch it happen. Let me shove this through less. All right. So here is it's making some comments to itself, kind of. Here's the pre-processing stage. It's all right, here we're doing all these things. I'm in square.h. Then it's including. Sorry, I'm in main.cpp. You see it including square.h. Oh, sorry, no, we're in square.cpp. I'm scrolling up to the top. This is it, because I think I gave that first, right? I gave square.cpp first to G++. So it's not very often that I look at this. So square.cpp, that's the first thing that's happening, and it's noticing that in that file, in that file, we're going to include square.h. Why not? For fun. So you see it copying and pasting the square.h value here, the contents of square.h, after that file itself has been preprocessed. So these if and defs and end defs are going away. It's really just this line with some empty space around it that's being copied in from square.h. And it's these are recursive levels of inclusion almost. You can kind of think of it that way. Now we're back in square.cpp, and like that's the rest. So after the include line, we got square.h actually copied over, and now here's the rest of that. All right, so that's the first thing that it sees. And then it also, we gave on the command line just main.cpp. So it also sees that file, all right? And it's going to, all right, include some default things that it always includes, as well as then it's going to start doing our things. Square.h from line 1, it remembers that. So it's going to go and like include that, which is going to copy and paste it in, all right? So it'll do its header file guard stuff, just make sure it's not being infinitely included. And then you see it actually copying and pasting the contents of the pre-processed square.h file. Isn't that fun? So yeah, that's the idea. And yeah, then we go and have the rest of main happen. Isn't that funny? I've looked at the word square so much now it looks like it's spelled wrong to me. Hopefully that's not happening in your brain too. So yeah, that's the preprocessor. It's just going to fill in things and make an actual file for the assembler to get, like with everything worked out. Okay. You can also, so the header file guards we kind of talked about, it's going to like make sure you're not infinitely including things, but these go away. They just define a little special constant to make sure you're not infinitely including things. Let me just show you define. I had that before. Let me add it back in. Define, you can make your own special preprocessor level constant. So instead of this line, let's do something like this. Int x equals square of some fancy constant. All right, so I'm going to define a constant. Define Lawton, that's usually all caps. Lawton's favorite number. And it'll be 42. All right, and so I'll call this with Lawton's favorite number, and this is a preprocessor definition. This is not like a variable in C++. It's just going to see this, and anywhere else, it's just going to paste 42 in whenever it sees this. So like you can change it in one place, and it's just like part of the code. So let me show that working to you. If I run g++-e again, we can just do it on main.cpp. So here it is. We're in main.cpp at the top level. It's including square.h, so it's going to pre-process this and get rid of the header file guards, make sure we're not infinitely including ourselves. And so like at recursion depth 1, it's going to include the contents of the square.h file. There it goes. Then we're back in main.cpp with the rest of stuff. And you see that it's calling square with 42 because this definition got replaced and placed right there. Isn't that interesting? So that's pre-processing in a nutshell. It's just stuff that happens to your code before we're handing that code to the compiler. We're not ready for the assembly yet. We have to like find and replace all these things, for example. All right? So that's the preprocessor. Next, I want to talk about the front end of, like, I want to break down this compilation process. Let's zoom into here. Okay? So the front end of your compiler, hopefully you can imagine that implies the existence of a back end. But the front end is just looking at the code. It's like reading all the characters, like, oh, number sign, oh, I, all those things, right? Or those will be preprocessed away. So like, oh, int space, main, open paren, close paren. It's trying to figure things out. Like, okay, this is a function definition. How does that happen? All right? That is the front end of the compiler. It's looking at just the stream of characters, and then it's figuring things out about those streams of characters. So there's a few stages to the front end, and I'm zooming in for a reason. So the first stage of the front end is called lexical analysis. So you got all your tokens, or sorry, your characters. These are just like the textual characters of the file that's being compiled right now. I and then F and then all those things. We're handing those to this thing called the lexical analysis phase, which is going to group those characters into what are called tokens. So like, oh, I and F together, that's the if token. So that's what it's going to spit out. Like, oh, that's just one thing. Oh, open paren, it remembers that. NET, that's an identifier. Oh, okay, I'll save that as an identifier name. Oh, that's a greater than symbol. I'll remember that as a symbol. Oh, 0.0, that's one big floating point number. I'll remember that as one chunk of things. So that's what it's going to do. It's going to like group identifiers, operators, all those fun things together. And then once it has those, it's ready to be parsed. All right. So after you've done lexical analysis, then you do syntax analysis or parsing to make sure like, oh, yeah, it makes sure like that if needs like some parentheses after it in a condition. Like, are you doing it in that order correctly? all right? Honestly, the idea of parsing is to make a tree out of your code. So like if, what does if require? It requires, oh gosh, here we go. It requires a condition part and a body and potentially an else. So like that's the parser's job, taking these tokens, we call them. What does if need? It needs 3 things. Let's parse it up and make sure it's got them all. So if needs a condition, and we'll place the condition here. You can kind of read that condition as like a tree of operations. Like we're doing a less than operation on what? On its children, this variable and the 0.0 constant. You see that? That's really cool. And so if it parses, we can build this kind of tree. And like here's the body. You're going to do all these things, right? This line is going to do a lot of things to total. It's a plus equals. What are we doing? On the left, it's total. On the right, it's this big long string of mathematical things with like the parentheses kind of filled out. Like, all right, I'm going to be multiplying this by all this. So it's got like order of operations baked in. And then ifs can have an else case. There is no else case for this if, and that is allowable. All right, so it parses and it's correct. But maybe like if you forgot these, like these open and closed parens, like the parser doesn't know what's going on. Like if does not, it doesn't check out. I need, after the keyword if, I need an open paren, and it doesn't see it. So it will fail to parse, all right? And that's the idea there, all right? Once you got a tree, you're more or less home free, all right? After that, it's left to what's called semantic analysis, which just like, okay, you were able to fill in the tree. Like you have an if, a correctly balanced if tree. Does it actually make sense what you're trying to do? Like, okay, does this, is this net variable, for example? Is that a number that I can compare against with another number? Because maybe it's a string, right? And then you can't do the comparison. That's what semantic analysis is all about, all right? It's doing like type checking, make sure the types match, making sure that total can accept whatever this is going to produce. Make sure it's a number, for example, rather than like a string, okay? So yeah, that's a lot of words at once. I'm not going to really test you too hard on any of this, but like these are all the stages. Like, all right, figure out what these characters mean, group them into tokens, we call them, and then like, all right, figure out what these tokens are trying to mean, parse them into something that's closer to C++, and then like make sure that tree that we made, like that if statement actually is doing the right things. We're not messing up our types, like adding a string to a number or something. That's semantic analysis, the meaning. We're analyzing the meaning of what we've written. And then like if it passes all the stages, then you're ready for the back end of the compiler. All right, that's going to go and generate assembly code. All right, so yeah, I hope that makes a little bit of sense at least. It's kind of cool to think about. All right, so these trees, for example, this tree, these tokens, they are an intermediate representation of your code. All right, so this is another fancy term and some new ideas. So the back end of your compiler is, its job is to spit out assembly more or less, and that's architecture specific, right? And to also do optimizations that like, okay, if you do this load instruction and this move instruction, I can optimize that into something quicker, for example. So that's the backend's job, to produce assembly that is optimized, okay? So an intermediate representation is anything in between your original C++ text and like assembly, okay? That's kind of what's going to happen. So technically this tree, called a parse tree, it counts as an intermediate representation. This like vector of tokens also counts if you zoom back in. So those are called intermediate representations. A standard example of that is what's called LLVM-IR. I don't know how much I've told you about other compilers, but there's G++ to compile C++. There's also Clang++. That is a competing compiler. They're both going to give you a final thing. They work the same, but they're different, all right? And then GCC and then Clang by itself. Those are the C compilers. They're competitors, all right? Clang is part of the LLVM project. I forget what that stands for, but there is a type of intermediate representation that they like to use, their IR, intermediate representation. Here's an example of that. It looks kind of like halfway between C++ and assembly almost. All right, so here's like, it's going to translate this. Before it makes assembly code, it's going to translate it into this, which it's going to run some optimizations on first. All right, so here's like a square function. Here's the LLVM intermediate representation for that square function. And you can see like, oh, it's closer to assembly. It's got some more information. It's like, all right, 32-bit integers, it's keeping track of that. It's a function called square. It takes an int. That's a 32-bit thing. it's talking about the stack right now. There's no need to do this thing called unwinding. And then like it gives a label, so it's closer to assembly, right? This is the entry point of the function. What am I doing? Well, it's making some secret variables for itself. It's like it's allocating space for an integer, making sure that it's 4-byte aligned because I ran this on a computer that requires that, for example. Like that's what the class server needs, for example. And then it's like it's storing it. There's like a store instruction that's not really assembly yet. It's like store an I32 into a variable called num. All right, that's the idea now that I've made space for it. Make a temporary variable, store that in. All right, make another temporary variable, get ready for it. All right, store in the number. You got it in there twice, I guess. And then it's going to do a multiplication. So store into a variable called mul the result of multiplying temp with temp1. So it's like it's got the thing twice in 2 separate variables. It's just pretending it has infinitely many registers of any name that it chooses. So, and then it's like return as a 32-bit value that result of that multiplication, which I shoved into a variable called %mul. All right, that's kind of how you read it. It's like halfway between assembly and C++. And so there's some optimizations that can be done here now that we have more information about the code, and that are easier to be done at this level rather than the assembly level for like ARM assembly. So that's what it's doing. That's what it's keeping track of. And that's an example of intermediate representations. Obviously, I would never dream of having you memorize this, but that's just one thing that one kind of compiler likes to do. All right, it's a common thing though. In addition to intermediate representation, like a special kind is called bytecode. Like that's usually a final output of a lot of compilers. Some languages don't actually get assembly spat out for them. Crazy to think about. But C and C++, we produce assembly. Some languages don't produce assembly. They produce what's called bytecode. So Java is a good example of that. Java programs, when you compile them, you use a compiler. It's called Java C, right? You say Java C. It's called the Java compiler, but it's really creating bytecode. It's compiling to this thing called bytecode. All right. So for example, here is a function, and let me show you what bytecode looks like for Java at least. So here's a Java function that looks a whole lot like its corresponding C++ version. It's just like doing some fancy calculations on 2 integer values. It's square rooting them, doing some power operations. Their library names are slightly different, and then it's like chopping off the decimals for some reason, right? So the compiled form of that, like what Java C will do for you if you were to compile this program, it's going to spit out this code, and this is called Java bytecode. So like it knows, it like makes a little label. It's not really assembly though. It's a special thing. So it's like, okay, it's making sure that it remembers things, and here are the actual instructions. This is like an interesting kind of assembly. This is bytecode. This is the instructions on the Java virtual machine. Okay, if those words make sense to you, it's like, all right, load the number 0, convert that number to a double, then load 2.0. Load 2.0 somewhere. It's like doing it on the stack. This is a stack-based machine. Then make a call to math.pow, because we're just giving, like we gave the variable value, and then we gave 2, and then we're calling the function. It's like putting them there, all right? So that's what's happening. I guess, sorry, this is load argument 0, excuse me. Load argument 0, convert it to a double, because that's what pow wants, and then load 2, and then call the function. And then here it is doing the same thing with the other ones. Load argument 1, convert it to a double, and then place the number 2 again on the stack, and then call the function. It's like everything goes on the stack in Java. But this will get optimized away eventually. It's like, okay, take those results, add them, and then call square root on whatever that result was. So there's square root being called. Convert it back to an integer and return that value. So obviously I'm not going to test you on this. I was going through it fast, but that's kind of the idea. It's a different thing. It's its own little assembly language. This is not runnable on our CPU, but that's what Java C emits. So you need something in between. So you need what's called the Java virtual machine. You give your Java bytecode programs. It's like 1s and 0s. It's encoding this idea, but it's not quite runnable on the CPU yet. So you're going to give that to the Java virtual machine. Java virtual machine, and then it's going to run it on your CPU for you. All right, that's the goal. Okay, it's essentially translating on the fly. That's going to go and run on the CPU. It's going to do a translation into actual assembly. Okay, so that's the idea. So yeah, you need the JVM, the Java virtual machine, installed to run these bytecode programs, because like there's an intermediate step. It's getting kind of translated on the fly into actual CPU instructions for whatever architecture you're on, like Intel, like ARM. And so that's actually a good thing that people that use Java like. They like the idea that, okay, I'm going to compile it once, I get my bytecode for that program, and I can ship that to everybody. Everybody with a JVM installed gets to run that, because like it's the JVM's problem to like get it running actually on the CPU, if that makes sense. All right. But the con to that is like you have to like wait a while, because you have to, like, there's that intermediate stage. It has to get translated the very first time everything gets run. So it makes it a little bit slower. But that's a trade-off that certain people are willing to make. So that is bytecode. It's a kind of compilation result. All right, for languages that are not C and C++. All right, let's talk about how to make our programs faster now. Let's talk about profiling and optimization. Two sides of the same coin, almost, honestly. So profiling is a way to answer this question. It's like, why is my code slow? What is going slowly about this program? Where is my program spending most of its time? All right. So I've got a fancy example that I pre-made where I'm going to sum up a bunch of elements into an integer array. All right. I'm going to sum up a bunch of elements that are already in an integer array into a bigger place. So that's going to be profiling. Go into the profiling folder. There. And so I got these files. Let's look at sum v1. All right, so here's a silly little program that makes a giant array on the heap of a prime number size, 100,000,007, and it makes that many ints on the heap, and then it fills that array with just some random, with just values, right? The values that are in there, like with each index, I guess. We're filling that array, and then we're summing up all the values of that array. Here I am calling SumArray on that array with its size and printing out the sum. I have so many values they can't fit into a normal int to sum them, so I'm going to sum them into a long, right? We're going to return a long, which is a 64-bit value. So there's my result. I'm just going at every index and returning the sum of all of them, but I'm summing them in a weird way, okay? Here's what I'm doing. I'm iterating this many times, so I'm visiting every place, as many things as there are in this array, but I'm going at about those things in a weird way. I'm getting to each index in a very odd way. I'm starting with index 0, like adding that in, but here's how I advance the index that I'm going to look at. I'm going to advance it by another prime number, all right? Mod size. If you've taken 26, CSCI 26, you know that this will, in this weird bouncing around way, it will visit every index exactly once. So you're going to hit everybody still, but you're going to miss the cache every time, because like if your next index is like 50,000 ints away, then that's not part of the same cache line from the previous read to the array. Okay? So once you wrap back around in the loop, we're going to miss the cache a whole lot, and we're going to notice that in our profiling step. All right? So yeah, here's what's going on. We're stepping by that much. So we've got a size prime array filled with increasing numbers, and we're summing up all the values, but we're stepping in a weird way through the array. It's like we're doing this. Like we're reading from the array, we're reading all the elements, but like we're jumping around as we're reading them. And we wrap back around. We're eventually hitting everybody, if that makes sense. But we're just getting there in a weird way that's going to ruin our cache performance. Okay? So, if you would like to profile your program, one way to do it is to use G++. It's got a profiler built in. It will show you where things are slow. All right? Here's how you compile. You say G++ -G, and then you give -PG, okay? Profiling, okay? So, and then you just run your program as usual. So here's the program. Like we can compile and run it as usual. It's just going to take a while, okay? So if I do G++ sum v1, .cpp-o sum v1, like that's just the normal way of compiling it. And it takes a while to run this thing, okay? We'll watch it run. It takes a while. It's bouncing around, but it does get the answer right. That is apparently the answer, which is interesting to think about. So yeah, it's just a bunch of increasing numbers. And so we can profile this. Why did it take so long? That's our question now. So we'll give it to the G++'s profiler. So -G and then -PG. All right, hit enter, and that compiles it again. And now when I run it, it's been compiled in a way that it's going to, in addition to keeping track of, like, it's going to actually run the program still, it's also going to write to a special file that tells me information about how this program ran. All right, so I ran the program. If you notice, it generated this file called gmon.out. It's like monitor. It monitors the program. All right, and so there is a corresponding program that can read that file. All right, it's called gprofiler, part of the GNU standard library. Just like this is the GNU G++ compiler, C++ compiler. Okay, so if we say gprof, then the name of our program, that will show the profiling information. All right, so let me show that to you. So I say gprof on this program sum-v1. It will go and read all these things that it, like all the information that it kept track of in that special file, that gmon.out file, after I ran it that one time, and it's going to give me some information about that. If I scroll up, you'll see there's a lot going on here. Let me actually put this in, pipe this through less. So here's what it's saying. It's like, okay, 88% of your time was spent in the sum array function. 11%-ish of your time was spent in the fill array function. Isn't that interesting? That's really powerful that you get to see that. It's keeping track of that. So that's at the top. That's the first information. That's usually what you're looking for. It will show you even more about that, like granularity. What's some more stuff? Like this is what I spent my time doing. Here's some more information about that and kind of how I got there. I got to sum array from main. That call was taking up 88.3% of my time, and then fill array from main was taking up 11.7-ish amount of my time. All right, and at the very bottom, it's just like, okay, yeah, here are the two functions. So a lot of information. And this is a sample. It took a little sample, it like set a little stopwatch when the program ran. So if you rerun the program, actually, your program runs, like it's getting scheduled on the CPU. It's taking more time or less time. If you remember the old percentages, they're not going to be exactly the same. If I rerun it now, it regenerated this gmon.out file. So if I run that through gprof again, you'll see that it's slightly different. It's still 88-ish and 11-ish, but I think this one was more than it was before, right? It's a sample. It's taking a sample of your program as it's running. It's not perfectly accurate. It's just a sample. It's just statistics, but it's very helpful for us because it's telling us that, oh, sum array is taking way too much time. If we go and try and look for how to fix our program and make it faster, sum array would give us the biggest bang for our buck, and that's the job that a profiler does for you. It tells you like where you should focus your efforts. All right. So cool. Let's yeah, it's just sampling every 0.01 seconds and seeing like where is your program right now. Is it in the main function? Is it in the sum array function? All that stuff. All right. So let's I guess let's fix it. All right. Let's fix the issue and like iterate in a normal way and see how that changes things. So here I've made, instead of iterating in this horrible cache missing way, let's do it in a better way, sum v2, all right? This one's just going in order, right? Just adding up all the values. Surprisingly, you're gonna get the same answer, just thanks to prime numbers and math. But here's g++ sum v2, -o sum v2. If you run that, it runs noticeably faster, first of all, and it gets the same answer though, which is funny. So that's pretty cool. But now let's profile this. Let's see, all right, if I could improve this. I still want it to be faster. What could I do? Where could I focus my efforts? So again, I'll say G++. I'll compile it in the fancy way, -G-PG for profiling. And then when I run it, again, it's taking a sample, so it's not perfect every time, but like that was a sample, and it overwrote this gmon.out file. And so now if I say gprof on the name of the new program, right? Gprof on sum v2, it'll output its information, then I'll feed that through less so that we can iterate and look through it. Ooh, look. Sum array is now only taking 30% of our time. Fill array is taking the longest. Isn't that cool? Like, okay, this is optimized now. Now the bottleneck is fill array. Isn't that amazing? And it's a faster program for sure anyway. We've made it faster. So let me prove that to you. There's a way to just time your program. It's called, I think it's just time, right? That might just tell you the time. Yeah, okay, so if you say time, well, I wasn't planning on telling you this, but if you time your programs, you can just say time and it will run that program. Oh gosh, so time dot slash, pretend to run the program. So our first version, the horrible one, took 4.71 seconds. And then the second one took less than a second, 0.69 seconds. Isn't that great? So we already got a speed up. And then we look at our profiling information that was generated when we ran it. And we see, okay, here's what we could be doing better. All right. And if you want extra information, like it'll give you some more better granularity down here. It's like, okay, these calls were from main. Main's called a fill array. Main's called a sum array, because there might be multiple ways that you got there. So it's telling you how you got there and what's happening, what it saw. And okay, now fill array is taking longer. It's the bottleneck. Okay, so how could we do better? All right, fill array is taking longer. If you think that you're better than the compiler, and you might be for certain reasons, but not this one. But sometimes you might be smarter than the compiler. I want to show you how to put assembly, embed assembly into your C and C++ code. Because, all right, if fill array is taking longer, like this is as good as I can do for fill array, honestly, in C++. You can't really do any better than that. But we have a trick up our sleeve in assembly, right? We know that we could use SIMD operations to write to multiple elements of this array all at once. Remember that? That will give me a speed up, because that's going to do a bunch of things in one clock cycle. So, all right, if I want this faster, I have to go to assembly. All right, so if you think you're smarter than the compiler, and the compiler is being dumb right now, we've told it to not optimize anything, you can embed assembly code. So let's use some SIMD instructions to fill that array. So if I use like a V register, right? If I use like my V0 register, for example, that is 128 bits, and I have I want to do inty things, right? I want to do stuff with ints, and so every ints are 32 bits. 32 bits. And so that information taken together means that V0 can hold, it can work on 4 ints at once. I hope that makes sense. That was not the best place to write that, but it's cool. All right, it's working out. So here's the secret. Here's how you can give assembly code to your program, like inside of C++. You say ASM, like a name of a function, then you put some parentheses. You do end it with a semicolon, but then you put your assembly code within quotes, and then you use some colons. These are all optional things, these colon space things. The colons need to be here, but the things that you put after them could be just empty space, all right? After the first colon, you put any output operands, right? Things that will produce output, like register names that are going to get the result of something that are going to be used for output. Like you're putting stuff in them, like the result of something. And then another colon, you put your input operands, like the names of registers that are going to be used as input in this assembly line. And then you also, finally, you can put a list of clobbered registers, registers that you are messing with because you're potentially outputting to them. Okay, so let me show that to you. And that's in sum v3. So we're going to make fill array faster, because fill array is now the bottleneck. Let's go to sum v3. Let me show you my idea. All right. So size is not a multiple of 4. First of all, if we want to go 4 at a time, we have to make size a multiple of 4. So I'm just going to fill in the first part of the array and advance this pointer in a way that lets me be guaranteed to have a 4 multiple size. All right. So as long as size is not a multiple of 4, like I'm anding it like this, as long as that's not 0, then size is not a multiple of 4 yet. Just like add in the variable values, insert into the array in the correct way still. Like it's going to run at least like 3 times, potentially, up to 3 times. So that's very quick. Just like make sure size is a multiple of 4, and now I can go 4 at a time. Now I can do my SIMD operations, okay? So, okay, let's move on. Let's go down here. So here's what's happening. Here's what I can do. I need to, like I'm adding in I at a time, right? I'm always doing this. So this might take longer to explain than, definitely longer to explain than to run. So I'm trying to fill in R of I with the value I, okay? And if I want to do this 4 at a time, I better get I plus 1, I plus 2, and I plus 3 in like a V register, in V0, let's say. And the way that you do that is you can duplicate a value, put it into a place, and yeah, I'm going to use this value. So let's see here. This is hard to explain, all right? This is assembly instructions inside of C++. So I'm duplicating into V0 4 times the value that is in W0, and I use this percent sign to mean that the value I want in W0 right now is the value for I. I'm reading I, all right? And that's what needs to go in W0, please. Make sure that that is the value of I that I'm duplicating. Shove that into W0 before this runs, all right? So we're talking to the compiler like this. And so the first colon, I didn't put anything. We're not outputting to anything. That's optional anyway. I guess we're outputting to V0. We could have said that. And then the next colon is input things. What am I inputting from? I am reading, R for read, reading the I variable. And I'd like that to be placed in W0. That's the first thing, okay? In some sort of W register. That's where I'm placing that. And then another colon to say what I'm clobbering. So I'm clobbering V0 on this line, all right? So yeah, W0, it's honestly just a W register. It's like printf almost. It's like the 0 thing that I give here. It's just like going to be replaced with whatever register I read that I has been placed into. It's definitely going to be a W register because it's an int, all right? So whatever W register it was, that's I, all right? Use that and duplicate it, all right? So yeah, that's what's going on. R, just make sure that it's in a register by now, and we're clobbering V0, okay? So I guess this is technically not W0. It's just like it's being filled in with whatever this was. It could be W5 for all. It was the 0th thing that I wanted in a register, though, kind of. That's how you do that. And then from then on, like, all right, I need to get I plus, like, I need to add 1 to this part, I2 to that, 2 to that part, 3 to that part. And so here I am moving 0, 1, 2, and 3 into registers and putting them in like a certain part. Like you can address into your V registers, if that makes sense. I'm putting those into, putting 0 into V1, the first chunk, 1 into the second chunk of V1. So like I'm filling V1 like this. Because then I can offset it, right? With 4 ints, 0, 1, 2, and 3. And if I add V1 to V0, which right now, what I've done to V0 is I've said this. V0 looks like this. It holds I 4 times. You see how if I add these into each other, now it's I plus 0, I plus 1, I plus 2, I plus 3. Those are the values I want to put in the array. Isn't that cute? So that's what's going on with these. Just look it up in the documentation if you're really interested. I don't really want to take too long to explain it. But that's what's happening, and then I can add them up, put them all into V0 now. So V0 finally now holds what I want. In V0, it holds 4 different ints, I plus 1, I plus 2, and I plus 3. That's what's going on. So I am hand rolling my own SIMD assembly here, and then, all right, here's what I'm doing. All right, so what am I clobbering? Like no input, output, anything. What registers am I clobbering right now? I'm clobbering W3, I'm writing to that. I'm clobbering V0 and V1 as well, all right? And that's the idea, all right? And then, yeah, then like that's what's going on in that particular iteration. Now I've got what I want almost in V0, and then I'm doing some stuff, like then I'm writing back, right? I'm gonna have to write back with a store operation a bunch of times. But I also want to get ready with V1, like able to offset, because like the next things that I want to do are 4 bytes later, or sorry, 4 ints later. Now the next thing after this should be like I plus 4 goes in the next one, I plus 5 goes in the next place in that array. Okay, so I think you're just going to have to read my assembly and just trying to work your way through it. This is beside the point. I'm just showing you that you can do this. All right, so I'm duplicating 4 in V1. And then I can use assembly in C++ still. It's like, all right, now in a loop, as long as size is bigger than 0, I would like to store whatever's in V0 a bunch of times into my array, all right? And so like go to the address. %0 means if you put something here that you're reading from, at least your input places. I want to read, I want R to be in a register, and I want this to be the register that holds R's address, the 0th thing that I give here. Does that make sense? That's kind of what you're doing there. Nothing that I'm outputting to. There's that. And then I'm clobbering V0. all right? So %0 here is going to get replaced with whatever register that R is in right now, that the compiler chose for it, okay? And then, yeah, just keep on doing that forever, and then just add in, right? Like offset your I values by 4. So like right now they're these, they need to change because it's going to be increasing. So like just add 4 each time. And then you just filled 4 elements. So you can increment R by 4 ints later. That's the next place I want to write to. And then size should be decreased by 4 because I just messed with 4 elements at once. All right. So that's how you can add assembly to your program if you really wanted to. And all right, that was the old one. It was 0.69 seconds for the old one. Let's do the new one. And please just yell at me in office hours if you want to know more about this program. It takes a long time to explain. So now let's time this one. Let's run sum v3. We get the same answer, and it took half the time because of SIMD operations. Isn't that amazing? I love that so much. So we can also profile that. We'll be like, all right, G++, one last time, -G, -PG, and then we'll run it. Super duper fast if we time it. Sometimes it takes longer or less. It's about 0.35-ish seconds. It's twice as good. So that's really nice. And then if I do gprof on sum v3 this time, pipe that through less. All right, what's the problem now? Now it looks like sum array is the bottleneck again, just slightly, which is fun to think about. You can now do SIMD operations for sum array if you wanted to, make it even faster. Okay. So that's what happens. That's when you want to add your own assembly. If you think you're smarter than the compiler, all right, you can do that. But honestly, if you enable optimizations from the compiler, do -O3, it's going to use SIMD operations for you, all right? So let's try -O3 on v2 and compare that against our hand-rolled assembly v3 and see that it's going to be more or less a tie, honestly. It's like our fancy assembly versus theirs. If I do G++, -G, I guess I don't need that. Let's do -O3 on sum v2. That's CVP, -O sum v2. And then I'll do the same highly optimized version of sum v3. So it took our assembly and then it also optimized sum array to use SIMD operations. So if we look at that, we compare them. So time running sum v2, the optimized version. Or, yeah. Let me, actually I think what I want to do is here, let's call it sum v3 O3, sum v2 O2, so I can have the originals still. So let's go back and replace the originals in the right way, so you can have those too. So there's sum v2, the normal version, sum v3, our version that we made faster. But then if I run optimizations, it's really going to be a wash. So watch. It's time running sum v2 optimized. 0.08 seconds. Isn't that amazing? So it's way better. Like, don't ever think that you're smarter than the compiler unless you have a really good reason. And then the last one, just it ran super fast. Cool. So our assembly kind of helped out, but honestly, it's a wash. If I go in and run, oh gosh, sum v2. Did I do this wrong? So it's not sum v2 O2. It's sum v2 O3. Excuse me. O2 to sum v2 O3. So if you run it enough times, it's taking that much time, and then sum v2, sum v3, our version, it's the same. You see how it's the same there? So it's just going to optimize it all to essentially what we wrote. So it wasn't really necessary to do all this. It was kind of wasted effort, honestly. Because watch what happens. If I take this code and I send it to somebody, if we go and we look at the assembly for the optimized version, let's look at this together. Let's do sum v2, the one that didn't have any of this stuff. All right, sum v2. Let's go back to that. And we're going to run that. We're going to compile it with optimizations. Let's go back here, sum v2. Let's compile it with optimizations into that. But let's actually stop and only do assembly. Let's do -s. Give me the assembly for sum v2. The optimized assembly, though. Okay? So let's go and look at that. And you'll notice, if I refresh this, if I go and I look for sum and like fill, right? Where are my functions? There's too many things going on here. So there is fill, and notice how it's doing the exact same thing, like making sure that the size is eventually a multiple of 4. Until it is, it's doing that, and then eventually it's going to use v-registers and SIMD operations. Isn't that amazing? That's really cool. And it's going to do the same thing for, which is the sum array. There's the sum array. It's again going to like start it off, make sure everything's a multiple of 4, and then it's going to go crazy with the SIMD operations, v0, v1. All right, so it's doing it for us, honestly. But yeah, if you ever want to, you can embed assembly into your program. All right, and so look at my example if you'd ever like to do that yourself. But honestly, -03 is going to usually do it all for you, more or less. Sometimes, though, there's like a cool assembly operation that you know your CPU supports that G++ doesn't. And that's kind of when you want to take this out of your toolbox. Okay, so that's embedded assembly, and that's profiling. That's how you know, like, what can I work on right now? What can I make faster? All right. One last thing. Let's now talk about coverage. It's kind of the other side of that. All right. So let's talk about coverage. Like, sure, your program's fast, but is it correct? Okay. So let's talk about this in terms of testing, because usually coverage is about testing. I want to make sure that my tests cover my code. All right. Let's test a recursive factorial function. So let's go to that folder, coverage. Boop. So I've got some files here. I've got 2 versions of factorial with some tests. All right, so here's factorial 1, and here's what I'm doing. I've got this function fact. It's a recursive factorial, right? If n is less than 0, the recursion doesn't work, so throw a runtime error. Otherwise, if n is 0, it's your base case. Factorial of 0 is 1. Otherwise, the factorial of some arbitrary n is n times n minus 1 factorial. So that's the recursive case. That's a correct function. And then let's say we want to test it with our handy dandy assert true. So here are a bunch of tests. Testing fact 5, fact 2, fact 1, fact 0, making sure they all check out. All right? So G++, fact v1, fact v1. So there it goes. And yeah, they all passed. And so the question is, are these tests good enough? That's where coverage comes in. Do my tests hit all of my code and make sure like everything is being checked at least once? All right. So you can ask G++ to keep track of whether which lines of code are being run or not by giving -- coverage and also -g always for these things. That will generate coverage information when your program runs. So I'll compile it in this way. I'll say G++ -g -- coverage, just like that, and hit enter, and now it made a program that will generate coverage information when it's run. All right, so now I run it, and it'll make a ridiculous amount of data files. So right now, my folder looks like this. It's more or less okay. It's got this extra file got made just by compiling it, and then when I run fact v1, it made some more files. Got this one too. So yeah, it's got some extra files that just got made. Let's figure this out together. All right, so then these are coverage information files, and then I can run this file. So just like it was gprof for profiling, it's gcov for coverage checking. And then we can use that with the name of a source file to analyze how that file has been covered by the program. All right, so you say gcov, and then you give the source file name. So we were working on factv1.cbp. A lot of fact_v1 files now. Hit enter, and then it's going to do a lot, and it's going to look into every file that we included and like give us coverage information about those too. So like every file that we could ever get to, like including IOString and standard accept. It just like it gave us a bunch of files right now, some coverage files for everything, including factv1.cbp's coverage information. It's a little disgusting, but yeah, here's our coverage. Like we covered almost all the file. We ran some of the code we skipped, and we can look into that. All right. So it's going to make a bunch of gcov files, and you just want to look at the original one usually, the one that you just gave to gcov, the one that you cared most about. So let's look at this file, the source file.cbp.gcov. So factv1.cbp.gcov now. Let's go look at it. So many files just got made, but here's the file, right? Look at the original too. There's the original, and here's just added stuff, right? It's telling us, all right, we ran this program once, here's what's going on, dun dun dun. And it's telling you each time, like, okay, we hit this if statement 12 times, because this was recursive. And we ran it a bunch of times down here in main. We hit that 12 times, we hit the base case 4 times, we hit this recursive case 8 times, we ran assert true a bunch of times, we passed 4 times, right? Each of these lines got ran, like, it's technically double counting them because like this part is happening and then you're also doing the assert true call. It doesn't really matter, but like that's happening. These are all getting run. The lines that did not get run, you have number signs associated with them. So you can see like, oh, this line's never happening. I'm checking this, 12 times I'm checking this, but I'm never getting to this line. And so that should scream, oh no, I forgot a test case. Does that make sense? Like this line that checked for was our input bad in this way, it's never getting run. Ooh, and so that's something we care about, and that's going to help us. This is called coverage. We're checking the coverage of our code right now. Did our tests cover it? And then also, just for fun though, this is a good thing to not be hit ever. We also notice that our failed line, printing failed for a test case, never actually gets run, which is actually good for us. So that's something that we don't ever want to run anyway. But this line, that screams we need a new test. Okay, I hope that makes sense. So yeah, let's fix that. So yeah, it's counting the number of times a line is executed. You can see a count here. These are like the original lines of the file. And any number signs mean that line was not executed. There is no count. It's like 0, right? So let's add another test to hit this case, this negative input case, and then we'll retry everything. All right, so let's go to fact_v2.cpp, where I have conveniently kept everything else but added a test case to check that we threw an exception. It's kind of hard to add a test case for that, so I had to do something like this. It's like, all right, I'm going to run fact of -1. You can't really run that in assert true because it's going to throw an exception, right? That's what it's going to do. So I just need to like catch the exception and make sure it got thrown. So I catch any exception here, then I'll set this flag to true. All right, so I'll just use a bool variable and keep track of whether or not that exception got thrown. Then I'll use assert true to check that, like make sure we threw an exception for a fact of -1. All right, so that's my new test. It's just all these things together. And then I'm running my tests again, and let's check the coverage of this. So g++ fact_v2.cpp-o fact_v2, but I want to add, right, -g and -coverage, dash coverage. Boop. And so getting there, it's going to add some extra files, and I have to run it still. /fact_v2, hit enter, and we see our output still, which is nice, but it's also writing to these coverage files. Okay, so it wrote a bunch of them again. It overwrote some of them because they were being used in the old one too. But now we want fact_v2 dot where is it? fact_v2 should be .cpp.gcov. It hasn't been made yet because I forgot to run gcov on it. All right, so now you have to like take these, like it's kept track of its information. Now we have to actually have it run the numbers with the gcov file, gcov program on the file that I care about, fact_v2.cpp. So there it's going to go and run our coverage things, reset files, make this one, for example, fact-v2.cpp.gcov. Long-winded names, I know. So there it is. And if you scroll through it, you will notice that, oh yeah, that line's being hit. It's covered now. Okay? Isn't that beautiful? So that's coverage. That's very, very important when you're writing tests. And it looks like the one line of this file that's not ever getting run is the exact line that we never want to be run, right? The failed line. So none of our tests failed. That's a good thing. But any other line, we want to make sure is getting run. Okay? So yeah, everything else is being run. Everything else is covered. Maybe you want to run them multiple times, like this is not good enough for you. Like maybe you want another case, you want at least two ways to get here, but one is good enough for our purposes. And that's how you check that. Make sure that your test cases are good enough. All right? I hope that makes sense. So yeah, these coverage counts are also very useful for profiling, right? Let's go back to SumV2, our SumV2 program, the one that makes sense to us. And we'll look at coverage, because that will tell us like how many times lines are being run as well. And that's kind of useful. And that also tells you where you're spending a lot of your time. That's another, it's like a more fine-grained way of looking into that, right? So let me prove that to you. If we go back and we do the whole thing again, it's kind of another way of profiling. Let's go back to profiling, and we'll do, we're going to do a coverage check for sum v2. If I go back to sum v2, that was the normal looking file. And let's check it for coverage now. Let's do g++-g-coverage on sum v2.cpp -o sum v2. Hit enter. Let's run it to generate some files. And then I'll say gcov, right, on the file that I care about, which is sum v2.cpp, which will create a file. I know this is disgusting. sum-v2.cpp.gcov. And so I'll open up that one. Bam. And you can look and see how many times, more fine-grained control over how many times things are being executed. Like, okay, I'm spending a whole lot of time in this loop, right? You're running this 100,000,008 times. One more, right? Because you have to have that condition fail one last time. I'm running this 100,000,007 times. Oh, I should probably focus my efforts there. Same with sum array. I'm running this 100,000,008 times. Isn't that amazing? So that's important to worry about, and like that's more important than like ever doing, like caring about how many times, like this is only executed once. I don't have to, there's no real way to optimize that anyway, okay? That's kind of another way to look into the speed of your program. Like how many times am I running these lines? Like let me see if I can like make that smaller in some way, okay? So that kind of goes hand in hand with profiling, coverage, right? So yeah, I think that's all that I wanted to show you there. I have one last thing that I'm required to teach you now. Now that you know a lot of nitty-gritty details and tricks, which is really cool. So let me tell you one last thing about compilation. It's like we love to compile things separately. We like to use our GCC or G++ with the -c to make sure things are being compiled separately. Yeah. And then you just like link them all together at the end with just one final call. All right. That makes things faster. That's what all my make files have been doing for you. So normally, compiler optimizations, they happen only at compile time. They make like the SIMD operations. They like make sure your loops are as fast as they possibly could be. Those optimizations happen at compile time and not link time. Sometimes there are optimizations that you can notice and enable when your programs are being linked together after they've been made into assembly. So if you say this, you say -f link time optimization, F link time optimization, that enables link optimization during the linking stage. And here's an example of link time optimization. Here are two files that you can compile separately. You've got main.c and a.c. All right. So a.h is declaring these functions, sure, foo1, foo2, and foo4. Here they are in some order, I guess. Let me go to green so I can actually show these to you. And so here's main. What's main doing? All main is doing is it's, first of all, it's creating a new function, foo4. It's including a.h, and it is calling foo1. All right. So when we compile separately, like main.c into main.o and a.c into a.o, we're making machine code for foo4 for main, of course. I'm getting some weird error. Let me turn off the autosave while it's doing that. We're going to make machine code for this function, machine code for main, of course, and then machine code for this guy, and this guy, right? They're going to be optimized as possible, as much as they can be. But notice how there's some useless stuff here, because what is main doing? All it's doing is calling foo1, right? And foo1 is calling foo3. So we're never using foo2, we're never using foo4, but they're getting compiled anyways. Okay? And so they're just wasting space in the final linked executable. So if you enable link time optimization, what the linker will notice, not the compiler anymore, it's going to notice that, oh, I'm never using foo2. That's unnecessary. I won't include that in the final output code, in the final assembly code, the final machine code. All right, that's one cool thing. And then also, what's it going to do? It's going to do some extra fancy things. So yeah, foo2 is never going to work out. And then I guess foo3, it will eventually be called, it could call foo4. So foo4 is safe to be here right now, but actually it's not. It's not going to be used anyway. I was getting ahead of myself. So if you look at this, if you look at your variable, so foo1 is going to be called, okay. if we're never calling foo2, like this is our int I, right? I is 0 right here. If we're never calling foo2, we're never resetting I, and so actually this guy, this condition is never going to be true. We're never going to run this line. So we're never going to call foo3, okay? That means that foo3 can't be called because I is never going to have a chance to be negative because this would be the only function that made it negative. So now I don't have to include foo3 in my output. Isn't that amazing? Which also means that was the only way that foo4 would have ever been called. And so now foo4 is unnecessary to be in the final executable file. It's just wasting space. Interesting. It's like we notice that this line's never going to get run. Oh man, that's amazing, right? So you're deleting things, you're saving space. Okay? So at link time, the optimizer gets to see like how everybody's talking to each other, the interplay that's going on. And that will make your final executable shorter. This is an example of making your executable shorter. Like it's getting rid of code that's unnecessary. Like you don't even need this condition check anymore, honestly. The whole darn thing is unnecessary. So like that makes your programs faster, one, right? Because you don't need the check anymore. And then also shorter, all right? I hope that makes sense to you. So that's link time optimization. Instead of like optimizing each individual function separately, you can think of them as one big picture when you're the linker, okay? So that's the secret. That's what's going on there. So yeah, I hope that makes a little bit of sense. And that was just a lot of nitty-gritty details for the day, but they're here to help you, right? Especially this idea of profiling, like see where your time is being spent in your program. That's going to save your life one day when you're in industry. And then same with coverage. Everybody cares about making sure that they're test cases, right? You're writing tests all day long as a software engineer. You need to make sure that all of your tests are covering your code well. Like make sure that every line is being hit one way or another, all right? And so those are like the two pillars of software engineering, honestly, profiling and coverage. And so you know a lot about them now. So go forth, use your newfound knowledge, and I think that's all that I wanted to say in this lecture. So thank you for your attention, and I will see you next time.